Yes, and also thank you to Janet Reed for chairing this session. Um, Participatory design among educators, all different kinds of new technologies, 3D printing, laser cutting. I think there's a lot of things in the horizon that needs to be discussed, and as Janet said, hopefully you'll have some time to meet up with some of the presenters and discuss further some of the issues that they presented during this very short paper presentation. Honestly, to those of you who are not researchers or academics, I'll just say you the hardest thing to do when you're a researcher is to present your own research in only 5 minutes. So they actually did a very good job too. Thank you very much. We managed to find you some internet access, as you can see up here. Just forget about the code you have in your key hanger, and please, all of you, use this login here. The username is FabLabConf, and the password is FabLabConf. So hopefully you'll all be online in a few seconds. Okay, while we are getting ready for the next presenter, let me just use 10 seconds to introduce our next presenter and keynote speaker, because we are very fortunate to have Paulo Blickstein here. Paulo is an assistant professor from the Grad School of Education at Stanford University. Paulo is also the director of TLTL, which is Transformative Learning Technology Lab. Paulo is one of the pioneers within digital fabrication, especially within education. And we're also very fortunate that Paulo and his team at Stanford will be working with the Danish Fab Lab at School DK project throughout the next years. So Paulo, whenever you're ready, we'll be ready. I'll just say short information. Paulo will be talking about 30 minutes or so. And after his talk, Paulo has accepted to have questions from the audience. So if you have any nasty questions that you really want to ask him about digital fabrication in education, please do not hesitate to address Paulo in Paulo's talk. So, 30 minutes presentation. Yes? We will make sure that all the presentations, as far as it is okay with the authors, will be shared on the fablearn.eu site after the conference. So you don't need to sort of type everything down. Are you ready, Paulo?
Yeah.
Okay, cool.
Okay, well, good morning, everyone, and thanks, Ole, for the introduction. So today I'm going to talk about, Fab Labs, maker spaces in schools, if it's the final revenge of progressive education. Even though this is the title of my talk, I want to add a little question mark there and see, is it really the final revenge of progressive education? So before starting, I want to acknowledge my team, my students. Some of them are here, like Nancy and Alicia, and some might be watching online. So those are my graduate students, postdocs, and all of that. And there is someone I just hired that, I'm from Brazil, so I hope there's no one here that has a problem with that. So I will quickly talk about some of the things we do in my lab. So we started in 2009 this program called Fab Lab at School, which started to build fabrication labs in different countries, in different schools, middle and high schools. So we build labs in the US, then in Moscow, in Thailand, in Australia. Actually, they are here too. And now we're working here in Denmark, in Mexico City, and many other places. This is one example of this is our lab in Thailand. This is the lab in Melbourne, in Australia. And now that building labs is becoming a lot easier, we also shifting our focus more towards research and supporting people building labs. So we, in 2011, we started the FabLearn conference at Stanford, and then this year we are, in partnership with Ole, now doing it in Europe, This is the FabLearn conference in the US in October. If you want to, submit something or attend the conference, it's happening in about 4 months. And so this is another thing we do. The other thing is the FabLearn Fellows program, and there are 2 fellows here, I think. So this is a program. We have 17 fellows that we selected this year, and we'll select every year. And we, they share experiences. We are producing a lot of documentation to put online for free for everyone in the world to know more about the machines, their practices, assessments, and all of that. So this is an annual program, so some of you might be interested later. And finally, we're doing a project called Constructables, which is the curriculum part of this thing. So this is under development. It will be online in a little bit, and we invite you to try it out. It's not online, so if you search it, you're not going to find it because it's still under development. But the idea is to develop a curriculum for digital fabrication that is not the traditional step-by-step scripted curriculum that we find everywhere. So how can we rethink curriculum for these kinds of spaces we care about? If you're interested in this project or in any of the things I mentioned, I'll put an email there. I didn't ask the person if I could, but hopefully, where's Alicia? Yeah. So this is, if you're interested in this, you can email Alicia. If you're interested in trying, she's the project manager of this, and then we can later contact you. Well, anyways, so back to the main theme of my presentation. I want to start. This is something I found online. I want to show it to you. It's about a school that it's a math program that runs for 2 years. Students they meet 6 times a week. So, they study multiplication, division, fractions, and all of that. So it seems like a normal school that would find anywhere, except that this is a Florentine school run by an Italian master in 1519. So in 500 years, we're basically teaching the same curriculum. And if you want a further confirmation of this, this is from the Treviso Arithmetic, which is the first arithmetic book ever written in 1478, to train the Venetian merchants and, doing the math because they needed to do all this calculation. And the actual techniques for multiplication, division are the same that we use these days. But they just created this because they didn't have calculators. So, I imagine if we could time travel to the 15th century and give, these people calculators, they would just burn this book and say, this is completely useless now. But for some reason, we didn't invent, we haven't been able to time travel. So this was written 500 years ago, and it somehow perpetuated itself throughout the centuries. And even though we have super powerful computers in our pockets, we're still, spending years teaching, how to do long division and things like that. Well, so I'm talking about this because we talk a lot about the how of schooling, so new methods, so project-based learning or the traditional methods and all of that. But we don't talk as much about the what of learning, so the actual content. So, you can try out different methods and all of that, but if we don't change the what, if we don't change the content, it's really, things get really hard. Because the curriculum is so packed with lots of topics and things that we have to teach kids, that if we want to do something new, it's almost impossible to fit it in. So every time I hear people talking about 21st century skills and new things that you teach, like problem solving and engineering, computer science, and all of that. The first thing I ask is so what are you prepared to give up in the traditional curriculum? And people say, oh no, we can't give up anything. Everything is important. And then I say, well, then we have to be realistic. It's impossible to add lots of new things if we don't actually get rid of some of the old things. And this seems to be one of the hardest things for people to understand, is that, and even for this community, if we don't convey this message that it's impossible to teach all these new 21st century things if we don't make time for them, we're setting ourselves up for failure, because you can't really teach anything half an hour per week in an elective class that has like 10 students. So, we need to make time for those things, some serious time. And I think the good news here is that the what and the how, they are connected. So, I know people who would say, well, to teach math and science, you don't really need a lot of hands-on. You just need people to, know the formulas and know all the procedures and all of that. But it's really hard to find someone who would tell you, even the most traditional educator who would tell you, yeah, we should teach computer science, but we don't need, the students don't need to actually program. We can just teach it on a blackboard, right? Or people who would say, yeah, we can teach engineering and robotics, but they don't need to do anything, that we can just, have them memorize, engineering principles and all of that. So I think even the most conservative educator will have a really hard time arguing for instructivist approaches to 21st century skills. So that's where I think we have an opportunity, is to say to policymakers and to these people like, oh, if you really want these 21st century skills, problem-solving engineering and all of that, unfortunately, we can't use the traditional methods. We need to do something new. We need the hands-on experience. And I think we have a better chance of convincing them than in the traditional disciplines. So I think this is the good news. But, again, we need to make space for those new things. And for that, we need to tell people what we want to get rid of. Maybe not all of the math we teach is as important as these new skills. So we have to have the courage of really prioritizing what is really important. So, and finally, I want to say that a lot of people, it's very fashionable these days to talk about like revolutions in education. And I live in the Silicon Valley, and every other day, there is some person that comes to my office, say, oh, I have an idea, it will revolutionize education. I say, oh, and then I say, oh yeah, 2 days ago someone came here with the same thing. And I think when we talk about Fab Labs and maker spaces in schools, I think it's a little dangerous to engage in this kind of revolutionary discourse, saying that we're going to replace everything there is, we're going to radically change schools and all of that. Because this kind of discourse, even though I believe in this, it scares schools, it scares teachers, and they have heard this so many times that sometimes I'm afraid we will alienate them if we say, this is a big revolution, it will change everything. So I think instead, it's better to do a sort of a Trojan horse approach, where we say, okay, you can keep your traditional instruction, but we want a good chunk of time for this. So like 30% of the hours in a week, we want for projects, for project-based learning, for making, for fabrication, all of that. And the rest, you can just do your, instructional stuff, don't fire teachers, just do whatever you do. And then once we are inside the system, we can start showing results and showing that, kids are engaged, that good things are happening, that teachers are more excited to teach and all of that. And then, we can increase that percentage and all of that. But I think this is a better approach than always insisting on this discourse that change will happen overnight and revolutionary things will happen overnight and all of that. I don't think it's a very effective approach. Well, so another thing that I think is important is we should not forget that lots of people actually did research on making, on fabrication, on robotics, on programming, especially, people like Seymour Papert that you might all know, who invented the Logo language. And other people like Paulo Freire, like John Dewey, like lots of educators, philosophers that have been advocating these kinds of approaches for decades. So we should not reinvent the wheel. We should read what they wrote, and we should look at all the research and the implementation research that they've done over the decades. There might be a gap. Many of you might not know this research, but it exists, and it's a very good thing to know what went wrong in the past, so that we don't repeat the same things. So I want to encourage you to go online and Google Seymour Papert, read his books, the articles of people in his team, like Edith Ackerman, like Michael Eisenberg, and so many others that you find online. So I think this is important because as I see it, the maker culture and the maker movement and the Fab Lab movement, it comes from three different cultures that might be at odds with the cultures that we want to establish in schools. So the first culture it comes from is the maker fair, the Make magazine culture that you might know about. You know, lots of maker fairs everywhere. And what a maker fair culture is, it's much about flashy things. So, you know, we want to show in a fair the most like fancy project and all of that. But sometimes we end up caring more about the product and the process. And if a child doesn't have a flashy project that, you know, spits fire and all of that, she might be very intimidated to go to a fair and show a project that's not flashy, even though the project might be fascinatingly interesting. But, you know, it's not valued in that culture. The second culture is from museums and this kind of after-school programs that value speed. So in a museum, you have to be fast. You can't do a 5-hour workshop with kids because you have to move the kids relatively fast. You have to do half-hour workshops, 1-hour workshops, things that are fast because that's, you know, your business model. And so this is also at the core of the maker movement, the maker culture, this idea that we have to do things fast. And finally, the third element is comes from the hackers, the hacker spaces, and a lot of the MIT culture of hacking, which is what I call the sink or swim culture. So, you know, I went to MIT and I know well this culture. So the way hackers learn is, you know, you give them a problem, you give the student a problem, put the student in a lab with a pizza, and then come back the next morning, and he will have figured out everything by himself. He will go online, he'll learn how to program, how to do all kinds of things. So it's a culture that's based on self-directed learning, on, you know, this kind of sink or swim, like if you can't learn it, if you can't do it, you know, you're out of our little clan. And even though this works for, you know, an engineering school where everybody self-selects because they like to do this stuff, it's not a very good culture for schools because not all kids are hackers in that sense. A lot of kids, they need a lot of help to learn how to program and all of that. So I think those three things are things we should be careful about. First, this culture of, you know, everything has to be flashy and fit for a fair, to be shown on a fair. Everything has to be fast, so every workshop has to be half hour, and we can't go deep into anything. And finally, this idea that every kid is a hacker and we just throw them in a lab and amazing things will happen. Well, it's not really like that. We have to throw them in a lab and put a lot of people to help them learn. Otherwise, always the kind of same kids will learn and the other ones will be alienated. So this is a more kind of general introduction about things I think we should care about. And now I want to show some of the research that we've been doing in the labs that we have built and in other ones as well. So one interesting thing is that, you know, in the school-wide surveys that we did, we found some counterintuitive things. So one of the findings that I want to talk about is this. So comparing public and private schools, so very kind of elite schools and more, you know, low-income schools, we found that access to equipment is not that different. So it's not that hard for a school to buy a 3D printer or a laser cutter. So that it's not that expensive anymore. So you know, we expect it to be big differences there, but there aren't big differences, which was counterintuitive to me. What really made the difference was that in public schools, and this is in the US, but it might be similar in other places, in public schools, the teachers, they really can't deviate from the standardized curriculum. So they have this pressure to, you know, there's high stakes testing and all of that, so they can't really do much with that equipment. But in the private schools where there's more freedom and they can experiment, there is no pressure from the government, you know, we have to deliver exactly this curriculum, then, you know, we saw very different results. So what I found that was really determinant in the success of those labs was not like money to buy stuff, but it was the amount of freedom that teachers have to go to deviate from the standardized curriculum. So I think that's a very important lesson to think about how we want to implement those labs. It's not just about building the labs, but it's about giving teachers the space to use the lab in a creative way. You know, it doesn't really work if you build lots of labs, but teachers don't have space or time to do anything interesting in the lab. They can only do this half an hour every 2 weeks projects because they have no time in the curriculum. So that's one of the findings I wanted to talk about. And now I want to talk about some of the assessments and some of the evaluation that we did. So we developed some, we call maker assessments, which are paper or physical tasks that we use to see if people are learning something or not, right? So for example, one of we call Maker's Table, which is a table that we ask kids to describe how they would make something. So you can see this is a before and after. So you can see it's much more complex, much more interesting, much more detailed. And the second assessment we created is called the logic flow, which is a sort of a computer science description of how the device works, right? So you can see the before and after, how it's more complex and more complete. And here too, the before and after. So those are different devices. So in this example, this is a plant, a vase that can water itself when it gets dry, right? So, we developed lots of those assessments, and we gave them to lots of kids. And one of the interesting results I want to share is that we found, kind of looking at the data in different ways. One of the really interesting results was that the bottom third of the group, so the group who started with the least knowledge about, logic and programming and making things and all of that, that was the group that gained the most. So they gained almost twice as the top third group, right? So the idea here is that we managed to decrease the spread, decrease the difference between the low and high achievers. And I think this is really, what the important thing, because if we do a fab lab or whatever, and it increases the differences between high and low achievers, we're not really doing much service to anyone. So that's another principle that I want you to keep in mind, is that every time you're designing a curriculum or thinking about this, we should always be thinking about reducing the spread. Because, it's not really, we're not doing a service to kids if we just take the kids who are already good and make them excellent. And then the other kids who are not very good, we don't do much for them. So I think this is, and I can go in more detail on when we go to the questions about, why I think this happened. Another research that we did was about something we call the ordering effect. And, we understand why it's called flipped classroom. So we were interested in this idea, what's the real value of exploration and kind of, instead of being lectured at, of exploring a problem space before lecture, maybe about this flipped classroom movement, which basically tells, kids should watch videos at home and then they come to school and then we do projects with them, right? And this goes against every cognitive science paper you find, this idea that you should watch a video first and then, and we wanted to test this hypothesis. So what we did was to have, two groups. One group watched the video first and then explored, and the other group first explored and then watched a video about a particular topic in math. And this is what we got. That the group who first explored and then watched the video, they scored on average 30% more than the group who first watched the video and then explored. And we did, people were, maybe this is like, I don't know, this is a weird result. So we did 4 replications of this, and every time we get the same result. When kids explore first, they achieve more. When they get a lecture first, they achieve less. And we even went as far as doing a comparison where, they had this kind of construction kit, and we had like a little video professor telling them, now, put this part together with this part. So it was still hands-on, but there was someone telling them what to do. And in the second group, they didn't have the video professor telling them what to do. They could freely explore. And again, in this condition, we got the same kinds of results, that people in the listen condition that had the video professor telling them what to do achieved, again, about 30% less than the kids who were allowed to freely explore. So I think this is a really important thing for many reasons, and I'll go into that in the questions if you're interested. But a lot of the things we care about, having kids explore a problem space instead of just being lectured at, we're trying to put numbers into those intuitions and not only intuitions, but things we see in classrooms. And I think this is important also because there is a big movement to sort of industrialize education by producing videos and having kids just watch videos like zombies, at home, and then do some. And I think we need to have a stand on this on this issue. So, and one of those papers is already published, so you can see it if you're interested. Okay, so. Let me talk about one last kind of cluster of results, and then I want to talk about some projects as well. So we also did some surveys in the schools we work with, and we are doing hopefully one soon also in Australia, and they are here somewhere, and in Mexico with Nancy. And we looked at all these kinds of skills. So the general computing knowledge, general fabrication knowledge, the repair, confidence in repairing stuff, knowledge of simple machines and things like that. So this is what we found so far in 3 schools, 2 in the US and 1 in Mexico. So the first thing here is, we talk about digital natives, how kids are great with technology and all of that. But most kids, when we say they're great with technology, they're great at using technology. They're great at using computers, tablets, and all of that, which is the blue bar there. It's general computing, right? So those items, we ask them, how good are you with tablets, phones, all kinds of software and all of that. So they all score high on that. When we go to content creation, which is like creating a movie or a song or doing this kinds of media editing stuff on a computer, they score significantly lower, which to me is surprising because those tools, like a video editing software, is basically free, and it's in every iPhone or Android or whatever, or any computer, right? And still, significantly less kids ever create something using computers. But then when we go to fabrication technology, it's even more tragic. It's really low. It's about half of, for every 5 kids that can use a computer, 1 or maybe 2 can actually do something, some kind of project that's not a media project with a computer. But the interesting thing is that all of this was very consistent, even across countries, right? Even like in Mexico and in the US, in very different realities and all of that. The good news was that when we did pre and post tests on these kids, so we had a group that we did the survey before and after a Fab Lab kind of activity. And we almost we saw a doubling in the fabrication knowledge. So I mean, this is important for 2 reasons. One is that we see that just in terms of like constructing a test, the other things that were not done in the workshop, like content creation, general computing. So we're not teaching them how to use any, like Word or Excel or a tablet. It didn't really go up much. So it really, the increase in score was really in the stuff they were doing in the workshop. So that's good news because it shows that it's, there is some kind of causal effect between doing this and the increase and also you see it's a pretty big jump, and I will talk about a little bit later. Just for you to have an idea, this is how we score the questionnaire. So this is a question that gets a 4, which is the maximum, and that's a question who gets a 0, which is the minimum. So here we ask them, how can you build a sprinkler system that would react automatically to temperature, right? And then some kids, they have this super detailed explanation. Some kids have this very simple explanation. We also looked at many other things, for example, STEM career interest, and it went up significantly. Some things we expected to go up but didn't go up, for example, IQ beliefs or academic self-efficacy. Creativity went up, repair ability went up, and things like that. And I can talk more about this later. I want to finish talking about one new set of techniques that we're using to evaluate these kinds of environments that we call multimodal learning analytics. So learning analytics is a technique to use this kind of fancy machine learning and computational algorithms to look into learning. And the multimodal part is that we add things like skin conductance, gesture, video, multi-channel audio, and all of that. And we look at all these things. So for example, we do videos like this one, where we give kids a task and we videotape them, and then we do some image analysis on what those two kids are doing, and we track their hands and all of that. Or things like this, when we use gesture trackers, we give kids a task, and then we use gesture trackers to see what they're doing with their body, right? So this is just the gesture tracking data. And then we construct these plots where we look at like the stress levels, how much they are talking, how much they are talking to each other, and all of that. And then we can identify what's the optimum stress level for them to be productive, or what's the frustration, what's productive frustration, and things like that. And what are the best methods to teach those things that minimize stress or maximize dialogue and things like that. For example, we found that with my student Bertrand Schneider, that we found a correlation between the amount, how people move their arms, and their learning. For example, when they're moving both hands, we found that they learn more. When they are passive, they learn less. But especially when they switch between active and passive, that's predictive of learning. So that means that it's not just about kind of moving stuff around all the time, but it's about maybe thinking about what you're doing and then moving stuff around, and thinking about what you're doing and moving stuff around. So it can give us really great insights into what we're doing. So now people are showing me like a sign there. So I want to finish with this. Let's see how many examples I can show. So now I want to show what kids actually do. And so this was a project that kids did in, about 10 years ago in a workshop I did in Brazil. So this is a toilet that has two buttons, one for solid, one for liquid, right? And back then, I thought, oh, this is a really cool project, but like that's a kind of crazy idea, right? Then about 3 or 4 years later, I went to, this is the Nobel Museum. I mean, it just happens. The first time I saw a toilet like this, and this is after I flushed, of course. But I saw that idea exactly, in this fancy Nobel Museum place, which was a toilet with two buttons, exactly as the kids have invented before. This is a kid in Brazil that wanted to invent, a system to save energy in street lighting by having a speed bump that would generate energy. And people said again, "Oh, this is a crazy idea." And then a few years later, I saw that Burger King in New Jersey was testing an energy-producing speed bump. Almost like 5 years after that. This is a project that kids did in my lab, high school kids, for detecting if the living room is empty using lasers and then turning off all the devices. And then 2 years later, I saw this on Amazon, which is called Energy Egg, which is exactly the same idea. Like it has sensors and it detects if a room is empty and turns off all the lights. This is a girl from Russia, and she designed this keychain, the green thing here, with very strong magnets and the very high sensitivity magnetic sensor, the white thing there. So when you walk too far from your keys, it beeps and it tells you, you might be losing your keys. And as you might know, this is a new invention that, from Silicon Valley startup called, I forgot the name, Tile, yeah. So I just want to end by saying that, I think there is a lot of optimism in making and digital fabrication and all of that. And sometimes it's about people concerned that countries should be more competitive or kids should get jobs and all of that. But I think the most valuable thing, is about, we have had kids in schools we have them in schools for ages, and they have all these wonderful ideas, but the tools they have are very limited. I mean, they can do a little sculpture, a little poster, but I mean, their ideas die there, right? They die in the poster and all of that because they can't really make it. There is no time. What these digital fabrication technologies are doing is they are accelerating that process. So now it's conceivable that in 2 hours or 5 or 10 hours, a child can actually build an invention that works. And so all of these ideas are not just lost in the wind. They become real things. And as I just showed to you, those are good ideas that become products later. So I think the most amazing thing to me is imagine how the future will be, if we all of a sudden have like 100 million kids all over the world inventing things to solve problems in their communities, to solve problems in their lives, not limited anymore by the lack of tools, and using the amazing creativity that they have and the great ideas that they have. So for that future, I'm looking forward to. Thank you.
Thank you, Paulo, for a very interesting talk. We have time for questions now.
Taking the case of whether the learning gain is greater by first experimenting and then lecturing, or first lecturing and then experimenting, is the data available for different age ranges? And do you know is there a group of students who learn best the one way and a group the other way, which is just bigger, or is it a sort of random distribution? And is there some way you could make a pamphlet, takeaways for educators? If you do this, you will experience a learning gain.
Yeah, so most of the people that participated in the 4 experiments were about 17, 18 years, so they were either in the first year of college, I would say. But the results are very consistent. We haven't done, for example, an analysis of if there are different groups perform better in different way, but that's one of the things we want to do in future studies. But I think the explanation for this effect is that when you watch a video about something you know nothing about, it's giving you answers before you have the questions, right? So you're watching something like about statistics, you don't even understand why that's important, and when you explore something before, it might be a bit messy, you might not know all the stuff you're doing, but it's generating questions for you to think about. Then when someone gives you the information, then you say, oh God, that's what I needed. I needed to know this formula or whatever. So you're generating the need for learning that when you just get content before the experience, you don't have where to, if you want to think in kind of constructivist, you don't have where to store that knowledge because you don't have any structure to. So I think that's one of the explanations, right? You have to generate the curiosity a little bit, and then you can. But about the manual, I think it's a great idea, and we haven't been able to do that so far, but I think writing some documents that could easily communicate to educators, that kind of stuff would be very helpful. So thanks for that idea.
It was more or less the same question. You were talking about productive frustration, but also, what about the lower third? Could they stand this frustration, or did they quit when they were frustrated?
Yeah, so we found that different groups have a different tolerance to frustration. For example, novice kids and especially minorities and females that are culturally they don't identify themselves as technology and things like that. Unfortunately, the first experience of failure that they have in the lab, they disconnect from so they say, well, I knew I was not meant for this is not for me, and all of that, and they disconnect and they become kind of negatively frustrated, right? So when that happens, we need to have a person there, like an adult or a facilitator, helping them to avoid this experience of early frustration and giving up. You know, for example, sometimes we work together with them, and then the facilitator, you know, says, "Oh, this is really hard. I don't know what's going on. Let's look online. Let's ask someone." So the facilitator can model to the child that, you know, this process of learning when you don't know something. So it's not about, I'm not an engineering person, but it's, you know, we all are learning here, and we can not know things, and it's not a sign that you're worthless, right? So I think we found, and conversely, for the kids who have like a father who is, or a mother who is an engineer at Google or Apple and all of that, they are very used to this kind of, you know, they thrive under you know, failure. They are used to it because their parents put in their heads, you know, failure is good, you learn by failure, but other kids might not have this experience. So that's why I think it's really important to, when I say we can't just throw kids in a lab and expect great things to happen, because it does, you know, great things happen when kids come from home already with that predisposition. But when they don't, and those are the kids we're more interested in, you know, you need to have a person that understands how to avoid this issue.
Thank you very much for the talk. It was very interesting, particularly the gesture one that you showed, the gesture tracking. I'm wondering if you had a chance to look at their cognitive abilities, if there's any change on that, or telling them to think aloud while they are doing that to see how they are really thinking. Is that any work on that?
Yeah, so you know, one of my students, Marcelo, that in one of those pictures, he is doing his dissertation on what he calls principle-based approach versus example-based approach, right? So the idea is that sometimes when kids are building a structure, for example, a bridge, and you ask them to think aloud, right, as you're asking, some of them will say, oh, you know, this bridge, this thing I'm building is like a bridge I saw yesterday when I was driving with my father or mother, right? So it's the example-based approach. They remember examples from their own experience, and they try to kind of reproduce what they remember, right? But the more advanced kids, instead of thinking about examples, they think about principles. So when they are thinking aloud, instead of saying, oh yeah, I have a chair at home that, you know, looks more or less like this, they think about, well, to make this table, I need triangles, right? I need this kind of, you know, like something like this. Triangles are more stable than squares, and all of that. So he's, you know, looking at this particular cognitive ability to move from examples to principles, right? So they are not just visually imagining things and trying to copy them, but they're building, thinking about, you know, engineering principles that might actually work. So if you're interested, you know, I can send you a couple of papers, and he's finding out very interesting ways to make the kids go from the example-based to the principle-based approach.
Yes, thank you very much, Paulo, for your talk. I have a question on the Trojan horse that you mentioned before, and also it links to generating curiosity in the kids. But relating this to the Trojan horse is, how do you actually generate the curiosity in the teachers? They might be stuck in a traditional approach of saying, I'm the owner of the knowledge, I'm going to have to give it to the students. How do we facilitate them to get rid of this control and also become co-learners? Because that's one of the main problems.
Yeah.
How can we, what is your experience on this point?
Okay, yeah, first I'm sorry, I was looking for you like there. And it's not that I wasn't paying attention. So I think it's because the speakers, you lose the kind of acoustic, you know, when people are talking, you know where they are coming from, but with the speakers, it's like, it's strangely hard to, anyways, so I think there are a couple of things I want to say. One is that when you train teachers, when we train teachers, every time we train them in the same way that we would work with the kids, right? So we put them in the lab and we say, let's do a project. And then they struggle, they complain, they say, I'm a history teacher, I don't need to be here, and all of that. And they, bitch around all the time. They say they don't like this feeling of being kind of helpless and all of that. But over time, it's really like amazing to see the transformation when they start kind of getting into it and getting excited about it. It's almost like they forget their teachers, right? And they start being playful and doing things, and they don't know something, they go and ask people and all of that. So it's a real transformation. And after we debrief with the teachers, and they tell us things like, in my 15 years as a teacher, the last time I remember having learned something new was like, 20 years ago when I was in college. They realized that they are teaching so much that they're not learning anything more, and they lost contact with how it feels to learn something new, to be helpless, to be insecure and all of that. So I think that's a really important thing, because when they go work with the kids, then they understand what it means, how it feels to be helpless, how it feels to be. And then the second step that we do is to do workshop with kids and teachers together, so that they can go learn things together when they don't know something. And then the teacher, because it's a history teacher or a math teacher, but it's not a history or math workshop, it's like a fab lab, so they feel they are allowed to not know stuff, because it's not their expertise. And so that process of feeling like you're allowed to learn and you're not, you don't have to perform as a teacher, I think is very empowering. So that's how we did our training in many of the schools, is by exposing teachers to this, right? And I see Ole, but okay, I can, there are many other, I think this is a really important thing, and I can talk more about it later if you want.
Yeah, thank you.
Well, I know there's many more people that have sort of want to ask questions to Paulo, but Paulo is available. Actually, Paulo will also give a talk on Wednesday here. It's the very same spot. But let's all give Paulo applause. Thank you, Paulo.